morning class. We are doing gravitational force, the last part. I hope you've watched the gravitational force that was pre-recorded earlier before you watch this one. Okay, make sure you've watched part 3 of chapter 6 before you proceed to this one, because I'm not gonna repeat myself. Okay, so gravitational force is exerted on the sun by the earth and vice versa. Gravitational force is also exerted by the moon on the earth, vice versa, where gravitational force is also exerted by the earth on the moon, right? Gravitational force is an attractive force, which means that if the FG is pointing this way, it means that it is attracted to the moon, which means that the moon is exerting the force, vice versa. If the moon is attracted, which means that this is the FG exerted by the earth on the moon. Okay, so the FG of moon on earth to FG of earth on moon is equal, but in opposite direction. Okay, these are vectors, so they are in opposite direction. Okay, so we've talked about the equation to find the force of gravity, which is this guy over here, whereby F12 is just G, where G is the universal gravitational constant, and this is the number, mass 1, mass 2, and the radius between the two masses squared. So it is very important to know what the mass is and what is the radius before you proceed to using this equation. Okay, so remember our free body diagram. Let's say we have a ball on the ground. We have, for our free body diagram, we have R, which is the reaction force due to the surface of the ground. And we also have mg, where mg is weight. And anything that is on the free body diagram should only be forces. So what type of force is mg? It is gravitational force, right? So Fg is equal to mg. M is mass. This is gravity, or the acceleration due to gravity. Due to gravity. Okay, just putting it out there for later. Okay, so this is, so you know that force is equal to ma. Okay, so force of gravity can be calculated by using this equation, right? G equals to mass of object. So this is the equation for an object on Earth. So how do you use that equation? Fg equals to G, where G is just the universal gravitational constant. Mass of object, mass of Earth, radius of Earth squared. Now remember, the earlier equation was mass of 1, mass of 2, and then the radius between 1 and 2 squared. So why is it the case here? Why is radius of Earth the only radius here instead of the radius of Earth to the radius of the object squared? Why is it not like that? Okay, so if I were to follow F12, G, mass 1, mass 2, mass of Earth, let's say this is E, mass 1 to E, gravitational constant, mass 1, mass of Earth over the radius of object 1 to radius of Earth, right? So that is usually the case. However, the objects on Earth are really, really small, right? For example, the radius of Earth is this big, while a ball on Earth is this big, which means that our object 1 is much, 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 much less than RE. When it is much, 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 much less, you can simply ignore the radius. So what happens? The radius just becomes RE squared. Okay, let's talk about an example if this is not clear yet. Okay, so let's erase this. Let's say I have a ball that is of 1 meter radius So I am going to, okay, so I'm going to draw an Earth, but you will assume that this is super big, and I have a ball on Earth where the radius is 1 meter. Radius of ball is 1 meter, and the mass of ball is 1 kilogram. Then this is the radius of Earth, and the mass of Earth is given by this one, and the radius of Earth is given by this constant. Okay, so to use the equation that we learned earlier, F12 equals to G mass 1 mass 2 R12, sorry, it's R12 squared, right? Okay, if I were to use this in its original form, this would be F ball Earth G mass of ball mass of Earth over R ball plus R Earth squared. This is how you get the radius between the ball and the Earth. So this guy is RBE. Right? Okay, so that is now 6.67. Let's just not substitute that. So the mass of ball is 1 kilogram. The mass of Earth is 5.98 times 10 to the 24 kilogram over the radius of Earth to the radius of the ball. So the radius of ball is 6.38 times 10 to the 6 squared. Now my question to you, would this equation be equal if I were to neglect the radius of the ball? Okay, so let's see. If I were to neglect the radius of the ball, so this becomes 5.98 times 10 to the 4 over 6.38 times 10 to the 6 squared. Let's see what the answer is. Let me use my calculator really quickly. Okay, so I calculated the values for this. I did not multiply it with G because it's a constant. So the answer is 1.47 times 10 to the 11 for this guy over here if I use the radius of the ball in the equation. And if I neglected the radius of the ball in the equation, the answer is still the same. Why is that? Because the radius of ball is so small compared to the radius of Earth that we can simply neglect it. Okay, that's just math. If something is super small in the denominator, we can just ignore it. Okay? So for objects on Earth where the radius is so small compared to the radius of Earth, we can simply simplify this equation to become G mass of object mass of Earth over the radius of Earth squared. This is for objects on Earth. Now, what if the object is located far above from the Earth where the height is very far, right? Let's say I have a satellite over here. This is my satellite, and the typical height of a satellite is 36,000 kilometers from Earth. To use that equation again, how would I do it? So F of satellite to Earth is G mass of satellite mass of Earth over the radius of Earth to satellite. Now I cannot ignore the radius of the satellite now because the height is so far away from Earth. So the radius is actually from the center of the satellite to the center of Earth. So this is now my R12, the radius of the Earth to the center point of the satellite, even though that is not the radius of the satellite. We want to know what is the distance between the satellite and the radius of the Earth, the center of the radius, the center of the Earth, basically. Okay, so again, our equation initially was F12 G mass 1 mass 2 R12, and previously we had an example whereby the radius is like this, right? Now we are talking about the same situation, except that now this is Earth and this guy is satellite. So how would I calculate for the radius? It's the same thing. Radius from the center of the masses, that is your radius, r, Earth to satellite. So how do you find the r, Earth to satellite? It is the radius of Earth plus the height of the satellite. So this becomes RE plus height of satellite from Earth. Okay, so this is your RE. This is height of Earth, the height of the satellite from Earth, which gives you RES. Okay, I hope that's clear. So your equation is simply, now it's like this, which means that now it's GMS, mass of Earth, R of Earth plus height of the satellite from Earth. Okay, it does not apply to just satellites, it applies to anything with very long height or very high height. Okay, you understand what I'm saying? So if we were talking about satellite, this applies. If we were talking about the Mount of Everest, where the height is so far from the radius of Earth, it applies. Okay, where the height is quite large or equal or almost the same as RE, you have to include it in the equation. Okay, so objects like ball, where their radius is so small compared to the radius of Earth, you can ignore it. Okay, so here this equation, they neglected the mass of object because they are just showing you the acceleration due to gravity. Remember, Fg equals to ma. So a is the acceleration of gravity. Okay, so this is the same dude over here. If I were to multiply it with the mass of object, this equation will be complete. Okay, it's just an equation for acceleration. It's the same thing basically, without the mass of the object. Okay. Okay, so using this approach, the acceleration of gravity on a planet in the universe can be known if the radius and mass of the planet is known. Then the acceleration is given by GH, where this is the acceleration of acceleration on the planet, and this is G, universal gravitational constant, mass of the planet over the radius of the planet square. Okay, so if there is an object on the planet, this would be MO, mass of object, gravity on object, times with MO. Okay, so it's the same thing. So previously we talked about MO, G, where G is M, mass of Earth, mass of object, over radius of Earth squared. It's the same equation, it's just saying, what if we are talking about another planet aside from Earth? So the equation, the same equation still applies as long as you know what the mass of the planet is and what is the radius of the planet. So let's do an example. Calculate the force of Earth's gravity on a spacecraft. Okay, so it's asking Fg, and we know Fg is G mass 1, mass 2, R 1, 2 squared. That is our basic equation. Okay, so the question is asking, calculate the force of Earth's gravity on a spacecraft that is 12,800 kilometers, and it shows here that it is twice the Earth's radius, above the Earth's surface if its mass is 1,350 kilograms. Okay, so this dude is in kilometers, you need to convert it to meters. Convert to SI unit. Okay, I failed to mention that earlier. You always have to convert it to SI unit. So mass, kilogram, and distance, meters. Okay? So let's try to understand this problem. So I'm on Earth, and I have a spacecraft. Sorry, let's do this down here. So this is my Earth. And then I have a spacecraft. What is it? A rocket? Okay, a rocket doesn't look like that. Just imagine that's a rocket. So this is the radius of Earth. And this is the height of the spacecraft, which is 12,800 kilometer. Okay, so it says here that 12,800 is twice the radius of Earth, which means that this radius of Earth is 6,400 kilometer. Using this equation, my radius is from here to here. This is R12. So, and to be more specific, this is RE to the spacecraft, RES. Right? So RES is 12,800 kilometer plus 6,400 kilometer, which gives me 12,800 plus 6,400, 19 times 1,000, 19.2. So this is 19.2 times 10 to the 6 meter. So that is the radius between the Earth to the spacecraft. So what did I do? I added the radius of Earth to the height. So this is just RE plus H. Okay, so this equation is now G, mass of Earth, mass of spacecraft, over RES squared. Okay, RES is R plus H, RE plus H squared, sama. Okay, so putting in those values, G is 6.67 times 10 to the minus 11. Mass of Earth is 5.98 times 10 to the 24. You don't have to memorize this. It will be given. And then spacecraft is 1,350 kilogram. It is already in SI unit. And your RES is 19.2 times 10 to the 6 squared. So this answer is, the answer is 1.47 times 10 to the 3 newtons. Okay, because this is force of gravity. So the force of gravity of Earth on the spacecraft is 1.47 times 10 to the 3 newton. That is your final answer. Okay, so what did we do here? We added the radius of Earth with the height of the spacecraft to get your RES. So it was basically this equation, okay? G, mass of Earth, mass of object or the spacecraft, radius of Earth plus the height of the object squared. Okay, so next question. Okay, an astronaut standing on the surface of Ceres, I don't know how to pronounce this, the largest asteroid, drops a rock from a height of 10 meters. So he's on a planet, he's on a large asteroid and he drops a rock from 10 meters. Okay, from 10 meter height. It takes, the time taken to reach the ground is 8.06 seconds. Calculate the acceleration of the gravity on Ceres. So this guy is S equals to 10 meter displacement going down. T is 8.06. It's asking you what is the acceleration. And I can use my kinematic equation to solve for this. S equals to UT plus 1 over 2 AT squared. Okay, so he drops the rock from rest. It does not start with a velocity. It drops from rest because he's just dropping it. So the initial acceleration, the initial velocity of the rock is 0 plus 1 over 2 acceleration or the gravity on Ceres times with squared, times is squared, so 8.06 squared, and S is your height, which is 10 minus 10. So the acceleration on Ceres is 0.3 minus 0.31 meter per second squared, which means that the acceleration is going down here. That is the direction, but the magnitude is simply 0.31 meter per second squared. Just like we had gravity is 9.81, the gravity on Ceres is 0.31 meter per second squared. This is for Earth, and this is for Ceres. Okay, so now it's asking you the mass of Ceres if the radius of Ceres is 5.1 times 10 to the 2 meter. So we know what GC is, the acceleration on Ceres is, and using the equation that we learned earlier, which was this guy, without the mass of object, so G equals to capital G mass of planet over the radius of planet squared. So if I were to use that, F gravity equals to mass of object times gravity on planet Ceres equals to G mass of object mass of Ceres over the radius of Ceres squared. Because I can't remember the equation of acceleration, so I'm just going to write the full equation. This is the radius of the object to the planet, and we know that the object is super small compared to the planet, so we are just using RC instead of RC plus our object. Okay, sorry, it's not a planet, it's an asteroid. Okay, so mass of object can be eliminated here to give me GC, gravity, RC squared. Okay, so GC, we know that it's 0.31 equals to 6.67 times 10 to the minus 11. The mass of Ceres is, we don't know, the mass of C, and the radius is 5.1 times 10 to the 2. So using this equation, we can solve for MC, and MC is simply 1.21 times 10 to the 15 kilograms. Alright, so that is it for your problem for this chapter. Alright, so I will see you on chapter 7. See ya.